Hello viewers and welcome to Pioneer of Success. This video is focused on understanding the energy transitions that happen in different types of spectroscopy and how it is different in case of the Raman spectroscopy. So according to Niels Bohr model of atoms, the electrons are rotating around the nucleus in certain quantized energy levels that we termed as the electronic orbitals. So these electrons has the freedom to move from lower energy state to a higher energy state, causing the molecule to excite to a excited state, provided it is supplied with some external energy, may it be form of light, heat, mechanical forces, or electrical pulses. So in case of the spectroscopy, the external energy source is the photon of different energy in the different region of the electromagnetic spectrum. So when the molecule is excited with excited with a photon of a particular energy, it could cause the change in the energy state of the molecule. May it be in the form of electronic state, the rotational state, which causes the rotational motion of the molecule, or the vibrational state, which causes the vibrational change motion changes in the molecule. So these overall energy state of a molecule is represented in terms of the energy level diagram, where the electronic transition is represented in terms of electronic states and the vibrational motions in terms of various vibrational energy states, and the rotational motion in terms of various rotational energy states. So if we could see, the electronic transitions take the highest energy, then comes the vibrational state, and then comes the rotational state. So for the electronic transitions to happen, we need higher energy photons as compared to that of the vibrational, and further lower energy is required in case of the rotational motion of the molecule. So if we consider different kinds of spectroscopy, different energy of these photons are supplied with. For example, if we consider the UV visible spectroscopy, as the name suggests, the photons in the UV visible region of the electromagnetic spectrum is used. Now, since this UV visible region of the electromagnetic spectrum is high in energy and low in wavelength, these photons could cause electronic transition in the molecules, because these have the energy in the range of 1 to 10 electron volt, which is high enough to cause a electronic transition of the molecule. Now when this molecule gets relaxed from the excited state, it can release this photon either in the radiative processes like the fluorescence or phosphorescence, or in the non-radiative processes like the heat. Now these electronics transition of a molecule, when it is excited with a photon of high energy in the UV visible region, it actually tells us about the band gap of the molecule. So the UV visible spectroscopy mainly defines the band gap of the molecule that we are studying. Similarly, if we consider the infrared spectroscopy, it is the photon in the infrared region that is supplied with. So the photon in the infrared region of the electromagnetic spectrum has a much lower energy as compared to that of the UV visible spectrum, and thus this energy ranges in the 0.01 electron volt to 0.1 electron volt, which is not enough to cause the electronic transition, but it is enough to cause the vibrational energy change in the vibrational energy state of the molecule, and thus it defines the vibrational state of a molecule when it is interacting with a photon of energy in the infrared region. So what are the different types of vibrational motion that could cause, like the symmetric stretching, antisymmetric stretching, scissoring, twisting, rocking, or waking? These are the different types of vibration of the bonds that could happen in a molecule, which is signatured in case of the FTI, in case of the infrared spectroscopy, and thus it gives us information about the functional groups that are assigned to, and differentiates between the symmetric and antisymmetric molecular structures. Now in case of this vibrational energy transition, when it relaxes back to its ground state, it generally dissipates energy in the form of heat and not in terms of any other radiative processes. Similarly, if we consider the microwave spectroscopy, as the name suggests, the photons are in the microwave region. So these photons have much lower energy as compared to UV visible and has lower energy even as compared to the infrared region. And thus this microwave spectroscopy, the transitions that happen is in the rotational energy state. So it defines the rotation of the molecule. It causes a change in the rotation of the molecule, which gives us information about the precise bond length and the angles, and also defines the molecular geometry, whether it is linear, bent, tetrahedral, or so. And in case of this rotational energy changes, when it relaxes back to its ground state, it is also dissipated in the form of heat or any other non-radiative processes, but not in the form of radiative processes. Now, in all these cases of the absorption spectroscopy, what we have seen that the energy transition causes the energy transition are caused only when the photon of exact energy differences are supplied with. That is, so that is the energy transitions that happen, that may be in the form of electronic transition, the vibrational or the rotational energy states. The difference between the energy state, the energy difference between the energies of these states actually has to be supplied with. That is, the photon should match the difference in the energy state. But in case of the scattering, this is not the case as it is. So what happens in case of scattering is that there is a concept of virtual state. That is, there is no absorption of the photon takes place, rather it only interacts with the molecule. So what does this interaction is? So in case of the scattering, the photons interact with the molecules and it comes back to the either at its original ground state or it to a higher vibrational energy state. So if there is a change in the vibrational energy state of the molecule, then why it is not called as the absorption spectroscopy? Why it is not counted in the absorption spectroscopy? Why it is a different type? So let us understand this with the actual phenomena that happens in absorption and scattering. So in case of absorption, when a photon is incoming to a molecule, it gets absorbed and causes the molecule to excite to a higher energy state. Whereas in case of the scattering, there when the photon is interacting with the molecule, it is not used up, that is, it is not absorbed. Rather, it causes a change in the polarizability of the molecule. That is, it causes a change in the polarization of the electron cloud of that particular molecule. And it does not cause the molecule to excite to a new energy state. That is, the photon is not absorbed in exciting the molecule to a higher energy state. Rather, the molecule uses that photon to change the polarizability of the electron cloud, and when it relaxes, it releases this photon either in its original form that we call as the Rayleigh, and or it is in a different frequency which we call as the Raman. Now, in case of the Raman spectroscopy, if there is a change in the frequency, where does the difference in the energy goes? So this difference in the incoming photon frequency and in the released photon frequency is used up in polarizing the molecule. Now, if we compare the absorption and the scattering spectroscopy, in all cases of the absorption spectroscopy, the photon is absorbed by the molecule to cause an energy transition. Whereas in case of scattering, the photon interacts with the molecule and releases instantaneously in the 10 to the power 15 second time scale, and the change in the energy, if it is causing, is used in changing the polarizability rather in changing the energy state of the molecule. So if it isn't causing any change in the polarizability, it will be released as a Raman scattering process with a different frequency, and if it is not causing any change in the polarizability of the molecule, it was released as it is in the case of Rayleigh scattering, without change in any frequency of the released photon. Now, if we see the energy level diagram in case of scattering, we could relate that this virtual energy state is actually related to that to the change in polarizability of the molecule. Since this change in polarizability of the molecule is not actually a change in energy state of the molecule, that is, it is not causing the molecule to reach to any excited state, it is not represented in terms of any quantized energy level. Rather, it is a virtual state where the molecule interacts with the photon, causes or does not cause a change in the polarizability, and then it is released back. This phenomena happens in the order of 10 to the power minus 15 seconds, and thus it is instantaneous, and hence it is not represented in terms of any actual energy state. Now, if the molecule is interacting with the photon and there is no such change in the polarization of the molecule, the released photon will have the same frequency as that of the incoming photon. And since there is no change in the frequency, that defines that it is not interacting with the molecule, and thus we will not get any information about the chemical identity of the molecule. And but this kind of relay scattering is used in deciding the particle sizing or the optical transparency of the colloidal solution. Now, in the cases where the photon is causing a change in the polarizability of the molecule, the released photon will have a different frequency as that of the incoming photon. And this kind of scattering is called as the Raman scattering. And the difference between the frequency is used up in causing a change in the molecule. And thus, this energy change is not as such that that is related to the electronic transition, but it is very minimal energy changes. Since there is no change in the energy state of the molecule is causing, it lies in the vibrational energy state. And since there is a difference in the frequency of the incident and that of the released photon, that defines that there is an interaction of the photon with molecule, it gives us the molecular fingerprint and helps us in identifying different functional bonds, different vibrational state or the rotational state of the molecule. Now, one key notable thing is that in case of absorption spectroscopy, the difference between the energy state where the transition is happening, may it be electronic, vibrational, or the rotational, the photon has to match the energy, this difference in the energy. But in case of the scattering, there is no as such requirement of matching the energy of the photon with that of the molecular energy level, because the photon is only used up in causing a change in the polarizability of the electron cloud and not in causing any change in the energy state of the molecule. And thus, whether the photon is higher in the energy or the lower in the energy, it does not matter in case of scattering, but what only matters is that the incoming photon should be able to cause a change in the polarizability in case of Raman scattering. Hope now you could be able to differentiate what actually difference between the absorption and the scattering spectroscopies and how Raman spectroscopy is different than any other kind of absorption spectroscopy. So stay tuned. In the next video, we will be focusing on different types of Raman spectroscopy. Thank you.